learned in 5.2 about rate laws and how we could have first order, second order. It's whatever the power was from the rate law equation. Okay, so in this unit, we're going to talk about how does that relate versus time. So we can graph this information, our reactants, concentrations, and we want to have linear graphs. So because of this, we have integrated rate laws for first, second, and zeroth order that have linear models and tell us a lot of information about the rate law. First order rate laws, remember, have the equation is raised to the first power. So like you see from the example here, the one right there tells us that it is first order reaction. Okay, so this type of reaction means that if the concentration of the reactant were suddenly doubled, the rate of the production of products would also double. They are related in that way. Well, we have what's called the integrated rate law, and that's this right here. It's in the form of y equals mx plus b. Okay, so the natural log of the concentration is equal to negative k would be the slope, time would be x, and then the y-intercept would be the initial concentration's natural log. So what you need to know, and I would highlight this, that if you have a plot of natural log versus time in a straight line on a graph, then that means that it's going to be first order. So this is a way to prove that something is first order. Okay, and you can also rearrange for this bottom equation. We're going to use that later on in an example, but mainly you need to know that a line, if you have natural log of the concentration versus time and that gives you a straight line, it is first order. Okay, so let's see what that looks like. We're going to graph it. So example 3 has the decomposition of N2O5 in the gas phase in this form. Using the data given, verify that the rate law is first order and calculate the value of the rate constant. Okay, now if we go back really fast, remember we said that the slope is negative k. K is the rate constant, okay? So if we can make this linear and we can figure out that it's a linear equation, then we can find the slope of the line, and slope is opposite of k. So if we would just change the sign on the slope value to find the k value. Okay, so you can do this in your graphing calculator. You can do this in Desmos. I do it on Google Sheets because that's what I have queued up. So I've already inputted the time values and the concentration values. Okay, but to verify that it's first order, we have to graph the natural log. So we need to find the natural logs of all of the concentrations. Okay, so I will help you in class learn how to do this, but just for the sake of this video, we're going to go quickly through to get the values, and then when you graph it, you want to make sure that it is a line graph so that you see the actual line. And here we can see that we've made a linear graph. It's a linear function. So that proves to us, because it is a straight line and I have natural log versus time, then it is in fact first order. So that's all we have to do for the first part of this example. Now the second part, I said, if we know what the line equation is, then we can know the slope. Okay, so we need to do some y equals, or if you have linear regression on your calculator, you could do it that way. Or we could just do change and rise over change and run for regular slope people if you're doing it on the graphing calculator. So I'm just going to pick the last two data points. Now we don't use the regular concentrations, we have to use the natural log values. So I got this from my Google Sheets, where I am going to take the very last value minus negative 4.382 over 400 seconds minus 300 seconds. and that will be negative 0.00693. Okay, so we found the slope, but if we look back at how the slope relates to k, the slope is equal to the opposite of k. Okay, so going back forward to where our slope value is, we just have to change the sign on our slope to get the k value. So the value of k is going to be positive 6.93 times 10 to the negative third. You could leave it out of scientific notation if you wanted to. Either way would be fine. So that would be one way to prove that something is the way that it is, and then from your line you can figure out your value of your rate constant. Well, using in example 4, we're going to use the same data that we had in example 3, but we want to find the concentration of the N2O5 at 150 seconds after the start of the reaction. So we are going to go back to the integrated rate law equation, which is at the top of your page, and that is the natural log, and I'm going to insert our actual reactant here, not just using A, so that we know where this is coming from. And that's equal to the negative k times t plus the natural log of the N2O5 0. So that little 0 tells us that's when time equals 0. What's that concentration? Okay, so now we're going to solve for the concentration here when plugging in for t, 150 seconds, and we just solve for k from example 3, and we can look at the table to find the initial concentration of the NLN. Okay, so the natural log, we just solved for k, it was 6.93 times 10 to the negative third, times time is 150 seconds, plus the natural log, and if we go back to the table, when time equals 0, that's the initial concentration. So right here is the initial concentration because that's when time equals 0. Okay, so I'm going to plug in 0.1 for that last part in the equation. I mean, if you still had your data values open from your graphing calculator or Google Sheets, wherever you did your natural log values, you could just plug that number in instead, but I don't have that up right now. So the natural log of the N2O5, when I solved everything out, and you actually use that natural log button on your calculator, I can help with that in class if you need it, that is all going to equal negative 3.3425. Okay, well that's not our answer yet because we have to get rid of the natural log. So the inverse function of the natural log is second natural log, and that is that e to the x function. So we want to take e to that exponent. So that cancels the natural log, and then that tells us that the N2O5 is 0.035. And then brackets, we talked about this in the last unit, or the last section. Brackets mean molarity. So this would be another way to solve using the integrated rate law. You have some problems on the homework that once you figure out what order it is, then you have to use the integrated rate law like so to solve for a value. We can have half-lives. You might have done half-lives in math class. And we do study those for first-order reactions. So it's the time that's required for a reactant to reach half of its original concentration is called the half-life. We have an equation for this for first order. This is given on the AP exam on the equation sheet, so you will also have it for tests and quizzes in here. Notice how it is not dependent upon concentration. It's dependent on the value of the rate constant, K. Okay, so you can figure out the half-life if you know the rate constant, or you can figure out the rate constant if you know the half-life, plugging into this equation. This is the only half-life equation that we are given for all the orders, so that tells me that you won't be needing any other orders, rate constant, or half-lives for the AP exam. So a certain first order reaction has a half-life of 20 minutes. We want to calculate the rate constant and then how much time is required. So for A, all we're going to do is we're going to use that half-life equation, which is the half-life is equal to 0.693 over K. We're going to plug in our half-life value and solve for the rate constant, K. So we have 20 minutes equals 0.693 over K. Maybe think about it as cross-multiplying to help you figure out what K will be. It's not as simple as taking 20 divided by, but when you do solve, the rate constant is 0.0347. Okay, so that's A, what we needed. We just simply use the equation. Now for B, we want to know how much time is required for this reaction to be 75% complete. Okay, well, so this is where we're going to use that other equation that I had mentioned earlier, or that was on the bottom of page, or it's at the top of page 7, at the bottom of the slide, where the natural log, we have the ratio of the initial concentration over the concentration at the time is equal to the constant K times T. Okay, so we want to figure out what that ratio is of initial versus the actual to figure out what this is going to be. Okay, because we want to solve for time, so we're going to be solving for T in our equation. We just solved for K, so we're going to plug that in from A, but we need to figure out what that ratio is inside the natural log. Okay, well, 75% complete also mean that 25% is left. That is original, hasn't reacted yet. Okay, and with this ratio, we can think about it as percent yield, where in percent yield, it's actual over theoretical times 100 gives you the percent. Okay, well, for the actual over theoretical, the theoretical would be the initial concentration, because initially, like theoretically, you should use all of it, right? And then what's actually used is the A0. And so from that ratio, we know when you times by 100, it's equal to the 25% left. So to get rid of the divide by 100, then I'm going to have that the A over A0 is equal to 0.25, or 1/4. Okay. Now, what we do with this part right here that we've just figured out, we're going to invert it. We're going to inverse it, because up in this equation, the A0 has to be on top, and we currently have A0 in the denominator. So if we inverse, that means that we're going to have the A0 over A, and if the 0.25 was 1/4, when we flip it, that's going to be 4 over 1, right? So that means that the A0 over A equals 4. So then this value of 4 is what we're going to plug in for right here to solve for our time. And I need to try to squeeze it in, I guess. So the natural log of 4 equals the constant K, which we just solved for in A, 0.0347 times time. So then you actually hit the natural log of 4 in your calculator and then divide by the constant, and then time is 40. And you just, to know what the unit is on the time, just look at what the half-life unit was, and that was minutes. Okay, so this is just a different way of thinking about how to solve for it. Will you have one like this on the quiz? Not necessarily, but it's a nice little brain teaser for you. So we've just been talking about first order reactions. Well, second order reactions, instead of taking natural log, the integrated rate law for second order includes the inverse of the concentration. Okay, so maybe highlight this, that the plot of the inverse versus time will produce a straight line, and that is your proof that it is going to be a second order rate law. So if you plot the natural log and it's not a straight line, then by plotting the inverse versus time, that will prove to you that it is. And notice it's still in the y equals mx plus b situation. So here, the slope is equal to k. And so when you know the slope, you know k, you don't have to switch signs. That's how it is. Okay, so for example 6, we have this reaction for butadiene, and we need to prove if this is first or second order, and we need to find the value of the rate constant. Okay, so I have put this into Google Sheets to graph. So I have my information given from the table already typed in, and we need to prove if it's first or second order. So remember, first order is when it's natural log, second order is when it's inverse. So I will help you in class, but just for the sake of the video, I'm trying to speed this up a little bit. So I'm going to find all of the natural log values, and then when I graph time and the natural log values, that is not a straight line. It's almost, but not quite, a straight line. So that tells me that it shouldn't be first order, since it didn't come out as being straight. Okay, so then now let's try the inverse values of the concentration. Don't take the inverse of the natural log, take the inverse of the concentration. And then when we graph time versus the inverse, that looks like a straight line. So this proves that this inverse versus time is our proof that it is a second order reaction. So when we know what order the reaction is, that tells us a lot of information. Using the rate law, or the integrated rate law, and knowing how to solve for k, all right? So we said it's second order because it is linear. So it's second order. And then for the slope, for the second part, the slope equals the k. So we just need to find the slope of the line and make sure that you use inverse values or take the linear regression, whatever you want to do. I am just going to use the values. And when you solve for slope, it's 0.0614. So that is the value of the rate constant. Okay? So again, it's just really nice to be able to prove what your graph is going to be to help you with first and second order. For 0th order, the integrated rate law involves just the plain old concentrations. You don't have to do anything to it. So when you have a plot of regular concentration versus time, then that will give the straight line, and the slope will be negative k, just like it was for first order. So that's something that you just have to memorize. How does it relate? But when you look at the integrated rate law, it matches up perfectly with what the slope should match like. Okay, we're not going to graph one of these because we've already been graphing, but I can help you if you need to do that in class. If you have more than one reactant, to figure out the integrated rate law, what happens by experiment is we vary the conditions so that one of the reactants is small versus all the others, which makes the rate law get simplified. So it may start out as being something a lot more involved, like we learned in 5.2, but then it reduces down, and it has a different value of k. So that's why there's that apostrophe after the k, to show that that is like a reduced k, or special to that part. Last but not least, this might not show up very well in the video, but it is in your notes. This table is awesome. It is a summary of everything you need to know and how you get it from your rate law. So when you know the order, then it tells you the rate law, the integrated rate law, how the plot will be linear, what the slope is compared to the k, and the half-life equation. So this is just a summary. You need to know how to use this information for the quiz.